Hi and welcome to the lesson of partial differential equations. So in today's class, we are going to start a new topic on systems of partial differential equations. So we are interested in finding the closed form solutions of the system of PDEs. And now we have seen that in practical life, we have many complex problems where systems uh, of PDEs may arrive, and we need to solve these problems. And many of them are like complex systems. But sometimes if we have some normal systems that are easy to solve or that are easy to get analytical solutions, so we can find them by using some analytical methods. So here we are going to introduce a new method for this purpose is Laplace transformations. All right, so we are going to apply transformations on linear systems for partial differential equations, especially with the constant coefficients, right? So pretty simpler problems in early stages we will take, and then in the later stages we will try some more complex problems. So let's start with a problem that is given as u t plus vx equals 0. That is equation 1. And then we have vt plus ux equals 0. That's equation 2. And given some initial and boundary conditions. So the initial condition is u of x comma 0 equals e to the power x, and v of x comma 0 equals e to the power negative x. And then we have the boundary conditions that are v of 0 comma t equals negative sine of hyperbolic t plus cosine hyperbolic t, and v prime of 0 comma t equals negative sine hyperbolic t minus cosine hyperbolic t. And then for u we have the boundary conditions as u of 0 comma t equals sine hyperbolic t plus cosine hyperbolic t, and u prime of 0 comma t equals negative sine hyperbolic t plus cosine hyperbolic t, right? So given this information, we have to find a solution for this particular system. So let's start with applying the Laplace transformation. So applying Laplace transform on equation 1, that is ut plus vx equals 0. So it's ut plus vx equals 0. So applying Laplace on both sides, we will get as u minus u of x comma 0 plus dv over dx. Since we are applying Laplace transformation with respect to t, so u of x comma 0 is given as e to the power x. So we just replace e to the power x here plus dv over dx equals 0. We name it as equation 1, right? Then applying the Laplace transformation on the second equation, that is ut plus vx equals Laplace of 0. So here we get sv minus v of x comma 0 plus du over dx equals 0, where this v of x comma 0 is given as e to the power negative x plus du over dx equals 0. This is equation 2, right? Now see these two equations, that is equation 1 and equation 2. So we can see that it's nothing but coupled first order differential equation, ordinary differential equation, in fact. Right, so we know how to solve these equations. So simply, if we uh, use this method, if we differentiate this equation, equation 2, so we will get s dv over dx. We are differentiating with respect to x here, so it's dv over dx, right, minus it will be positive e to the power negative x plus d squared u over dx squared equals 0, right? And then again, if I differentiate equation 2, we differentiated equation 2, so 2 implies, and then if I differentiate 1, then equation 1 implies s du over dx minus e to the power x plus d squared v over dx squared equals to 0. Now we can just substitute here in this equation here. If I substitute du over dx from equation number 2 from here, now this equation implies that du over dx equals e to the power negative x minus sv. So I can substitute this here. So this one implies that s times e to the power negative x minus sv negative e to the power x plus d squared v over dx squared is equals to 0, right? Now, this is easily solvable, so it's second order non-homogeneous differential equation with constant coefficients. So we can easily solve these equations. We have a lot of methods to solve these kind of equations. So let's arrange this equation. So it will be d squared v over dx squared minus s squared v equals e to the power x minus s e to the power negative x. And then we have the homogeneous solution to this equation is c1 e to the power sx plus c2 e to the power negative sx. And the particular solution to this problem is, I'm writing it directly here. You can just compute it. That is a to the power x over 1 minus s squared minus s e to the power negative s over 1 minus s squared. And now the general solution to this problem will be v equals c1 e to the power x, that is by the superposition principle, plus e to the power x over 1 minus s squared minus s e to the power negative x 1 minus s squared. And if I further just simplify with the signs, so I will get e to the power x over s squared minus 1 plus this s squared minus 1 here, right? Now this is the general form for v, but this is a function of x and s, right? But we need to find the function of in terms of x and t. So first of all, we need to figure out these two constants. For that, we have the boundary conditions, and the boundary condition is given as v of 0 comma t equals to, if you look at the boundary condition, it is given as negative sine hyperbolic t plus cosine hyperbolic t. And if I take the Laplace transform of this boundary condition, I'm going to get negative 1 over 1 minus s squared plus s over, sorry, it's s squared minus 1. So it's s squared minus 1 and s squared minus 1 here. Now if I apply this thing here in this equation, so I will get c1 e to the power, so it's v of 0 comma t, not t, sorry, it will be s now because it's a function of s because the Laplace transform is applied. So e to the power 0 plus c2 e to the power 0 minus e to the power 0 over s squared minus 1 plus s e to the power 0 over s squared minus 1 equals a negative 1 over s squared minus 1 plus s over s squared minus 1. So this cancels out and we are left with c1 plus c2 equals 0. So the first boundary condition gives this equation. Now applying the second boundary condition, that is v prime of 0 comma t, that is simply negative sine hyperbolic t minus cosine hyperbolic t. So the Laplace transformation will give negative 1 over s squared minus 1 minus s over s squared minus 1. So first we need to find the v prime, that is the derivative of this equation, right? So the v prime for this equation is sc1 e to the power sx minus sc2 e to the power negative sx, and then minus e to the power x over s squared minus 1 minus s e to the power negative x over s squared minus 1. Now let just apply the condition into the equation. So it will be v prime of 0 comma s equals to sc1 e to the power 0 minus sc2 e to the power 0 minus e to the power 0 over s squared minus 1 minus s e to the power 0 over s squared minus 1 is equals to negative 1 over s squared minus 1 minus s over s squared minus 1. So again, this cancels and we are left with sc1 minus sc2 equals to 0. So this is the second equation. So first equation is c1 c2 equals 0 and second is c1 minus c2 equals 0. So solving these two linear equations, we will get c1 equals to c2 equals to 0, which simplifies the equation x comma s to this part only, that is negative e to the power x over s squared minus 1 plus s e to the power negative x over s squared minus 1. Now if we take the inverse Laplace transform to this equation to find solution in terms of t, so we'll get negative e to the power x sine hyperbolic t plus e to the power negative x cosine hyperbolic t. So this is the solution for vx comma t. Now similarly, in this similar manner, we can solve it for u of x comma t by just taking out dv over dx from here and plugging taking out dv upon dx from this equation, that is equation 1. So this implies that dv over dx equals e to the power x minus su. So we can plug this thing here in this equation, this one, and this one, and we can solve for u because that will be a simple second order linear equation in terms of u, right? So now this equation, if I write, it's let's write and solve this equation here. So it will be s dv over dx plus e to the power negative x plus d squared du over dx squared equals 0, where this dv over dx we can find from the equation above, that is e to the power x minus scu plus e to the power x plus d squared u over dx squared equals to 0. Now again, this is a second order linear non-homogeneous ordinary differential equation with constant coefficients. So we can easily solve this equation. And again, using the same procedure, I'm writing the solution directly. Solution for this equation will be C3 to the power Sx plus C4 to the power negative Sx minus e to the power negative x over 1 minus s squared minus s e to the power x over 1 minus s squared. And if I simplify the signs, so I will just get here e to the power negative x over s squared minus 1 and plus s e to the power x over s squared minus 1. So this is the general solution for ux comma s, but we need the solution in terms of x comma t. So use the conditions. So u0 comma t is given as sine hyperbolic t plus cosine hyperbolic t, and if I apply the Laplace transformation, I will get u of 0 comma s equals 1 over s squared minus 1 plus s over s squared minus 1. All right, and then we have u prime of 0 comma t equals negative sine hyperbolic t plus cosine hyperbolic t. And again, we will get u prime of 0 comma s equals negative 1 over s squared minus 1 plus s over s squared minus 1. All right, and if we apply these boundary conditions into the equation, so applying this first condition, this condition into the equation, we will get C3 plus C4 plus 1 over s squared minus 1 plus s over s squared minus 1 equals 1 over s squared minus 1 plus s over s squared minus 1. So this cancels out, and again we are left with C3 plus C4 equals to 0. C3 plus C4 equals 0, and then u prime is C3 e to the power sx minus sc4 e to the power negative sx, and minus e to the power negative sx over s squared minus 1 plus s e to the power x over s squared minus 1. Just applying the condition, this we will get is 1 over s squared minus 1 plus s over s squared minus 1, and that will be equals to negative 1 over s squared minus 1 minus 1 and positive s over s squared minus 1. Okay, so this cancels out and we will get again C3 minus C4 equals 0. So again, by solving these two linear equations, this one and this one, we'll get C3 and C4 vanishes, right? So the solution now is pretty similar. That is u of x comma s will be just this part. Let me show you just this part, right? E to the power negative x or s squared minus 1 plus s e to the power x or s squared minus 1. And now if I apply the inverse transformation, so I will get e to the power negative x sine hyperbolic t plus e to the power x cosine hyperbolic t. So this is the closed form solution for u of xt, and the closed form solution for v of xt is we already found that is e to the power negative x cosine hyperbolic t minus e to the power x sine hyperbolic t. And now we can simply verify this solution with the given equation and the given initial and boundary conditions. So equation 1 says ut plus vx equals 0. So ut equals e to the power negative x cosine hyperbolic t plus e to the power x sine hyperbolic t, and vx equals negative e to the power negative x cosine hyperbolic t and minus e to the power x sine hyperbolic t. And if I add these equations, so I will uh, get this cancel out, which will imply that ut plus vx equals 0. Similarly, we have ux plus vt. So ux plus vt will be, so ux will be negative e to the power negative x sine hyperbolic t and plus e to the power x cos hyperbolic t, and then vt is equals to the power negative x sine hyperbolic t minus e to the power x cos hyperbolic t. So again, this will cancel out if I add them. So we will get ux plus vt equals 0. And similarly, we can just simply check that u of x comma 0 is e to the power x, and v of x comma 0, v of x comma 0 is e to the power negative x. And then similarly for the boundary conditions as well, we can just verify the boundary conditions as well, right? So in this way, we can solve these kind of problems that are linear first order differential equations. So in the next lesson, we'll come up with one more problem and an advanced problem in comparison to this problem. And then step by step, we will do advanced problems. So thanks for watching the lesson. Goodbye.